What just happened? Okay, there we are. All right, good morning. Okay, let's see here. Let's get ourselves organized.
Good morning.
Good morning. So far, it's just two of us here. All right, let's see how it's going here. I guess it's still a little early yet. We got a couple minutes before we start. Yes. All right, looks good. Okay. Here, let me make sure I can screen share. Let's make sure we can have this work properly. Okay, that's pretty good. All right. Okay. So now there's three of us here. All right, looking very nice. Sunset on Earth. I have the sunset on Mars. Right, so here in my background, let's see, this is my left hand. So on my left here, over my left shoulder, that's Mars. And then over my right shoulder, this is Earth. All right. Okay. So we got Earth and Mars. Now sometimes the Earth looks like Mars when the air is full of smoke. But today it doesn't seem so bad. I don't know, it doesn't look like the Mars. All right, so let's go ahead and get started here. So let's see. What I'm going to do is I'm going to begin by by showing you the stuff that is in your Canvas shell for this week. And I'll sort of walk you through what's there. And, give you a sense of what we're up to this week in Physics 210. So what are we up to this week? We're in Module 8. And Module 8 is right here. Just kidding, it's right here. So let's see, what do we got in Module 8? So in Module 8, I have another fancy physics video. That's what these are called. I think I like using these fancy physics videos because I think they give a pretty good high-level summary of what's in the chapter. And you can almost get away without reading it, if you just watch the fancy physics video. So that's pretty good. So I think I'll keep using those. Occasionally I'll add some of my own, but I think the fancy physics videos are pretty good. Okay. So let's see. So by the time you've gotten through the fancy physics video, you can read through these sections here. So you notice how section 8.7 is missing. That's the one that deals with rocket propulsion. And so we're not really going to deal with that too much in this course. That's really more a thing for the people that do physics with calculus. They're interested in, or they're required to know that more than you folks are. So we're just going to skip over that 8.7, And as far as, getting through these sections, I'd say, today's Tuesday. So I'd say maybe by tomorrow, you should consider, um, you should have at least gotten through maybe 8.1 through 8.3, and then you can save 4, 5, and 6 for, later in the week, Thursday, Friday, Saturday. You can read through those. And of course, you don't have to read through every single thing word for word. The summary that you get from the video is pretty good. So you can almost get away without reading anything. Okay, so what's a little bit different this week is that what I'd like to do is, once you have at least gotten through the fancy physics video, I'd like you to jump straight into the quiz. Okay. Just to sort of check your understanding of what you saw in the video and maybe what you read. Um, so the thing is, though, is if you're, if you're saving 8.4, 8.5, and 8.6 for Thursday, Friday, then obviously you'd wait until then to take the quiz. And then in the meantime, we have our lab activity this week. So this is going to be a simulation activity. So let me just quickly show you. So what we're going to do is we're going to run a special simulation that is implemented inside of an Excel spreadsheet. And here, let's see if this works. Okay, so if I open this up for a second here, I just want to give you a sense of what's in store for you. Here we go. So the simulation is produced by this fellow here, Franco Normani, a Canadian engineer. And so you see what this fellow has is he's got this projectile motion simulator and, blah, blah, blah. And, what he did was he basically programmed all of the physics into an Excel spreadsheet. Okay. And so, so what you're going to do when you do the activity is that you're going to, so basically, let me back up a little bit. What I did was I downloaded Mr. I forget his name again. I downloaded this fellow's spreadsheet. Okay. So I downloaded this document. And then I made a few small modifications to it so that we could use it easily for our activity. Okay, so what you're going to do when you do lab is you're going to open this spreadsheet and you're going to enter numbers in there and hit enter, right? And then it's going to simulate a projectile being fired. Okay, but it's going to simulate it with all the physics of the real world, right? So there's going to be air resistance, there's going to be, other stuff. And so it's not going to, it's, and everybody who does the simulation is going to get slightly different results because there's the element of experimental error is in there too, right? So that's what we're going to do. So, notice that there's 2 Excel spreadsheets this time. So so one of them is just for the simulation, right? So you just run that and you get your numbers out of it. Then I want you to take the numbers that you get out of this and put them into this spreadsheet. And, that's what you do for your graphs and whatnot, okay? Wait, do you make graphs in this? No, I don't think you make graphs. You just do some, take some averages, that sort of thing. Okay, all right. So, okay, that's all I want to say about lab. Oh, and lab this week is going to be Thursday as usual, except so I'm going to be the lab instructor for both sections this time around because Professor Hein has something else she has to do. Okay, so I'm going to be with you the whole time. Okay, So that's lab this week, and you can start the lab activity anytime. You don't have to wait until Thursday to start it. It deals with projectile motion, right? This is physics you've already seen, so you can dive right in. You don't have to read this stuff first. You can just get right into it. Okay, then we have the homework set. We do have a discussion. The discussion deals with physics that we saw the week before last. Okay, so this is a week in which the discussion topic is not the same as the topic, the theme of the module, right? So the theme of this module is linear momentum and collisions, but the discussion has to do with potential energy when you stretch a spring or compress a spring. So, that is what it is. Okay, and then last of all, I don't want you to forget, I have a survey here, another How Am I Doing survey. Main thing here is we're going to ask you if you still have physics anxiety, or maybe you do now and you didn't before. Basically, to ask you if you have any level of physics anxiety. And then the other thing I want to ask is, whether you like all the YouTube content, if you find it helpful. And then the third thing I'm asking is how you feel about the midterm exam. Was it too difficult? Was it too easy? Was it just right? And that sort of thing. Okay, so, this is completely optional, but, it does help me, provide a better physics course. If you do actually honestly answer the questions. So, please don't forget to do it. But of course, if you don't do it, it's no big deal. It's not a requirement. Okay. All right. So any questions about the overview of what's in Module 8? All right. Okay. So besides giving you a sort of overall overview of what to expect in Module 8, what I wanted to do was, talk to you a little bit about the physics that we're doing in this module. So let's take a look at that. So what is the physics that we're doing in this module? It's known as linear momentum and collisions, right? So we're talking about the physics of momentum and the physics of what happens when things collide. So here, what I'm going to do now, so I'm going to take us over to the whiteboard, and I'm going to write some things down for you to look at. All right. So let's see what we got here. See what we got going on over here. All right, so let's take a look here. Right, so this idea of momentum and collisions is pretty important in physics, and and so it does warrant me spending some extra energy to to get it across. So that's what I'm going to do. So this is linear momentum. Okay, so let's talk about linear momentum first. We'll get to collisions a little bit later. Okay, so what is momentum? Okay. Yeah, so what is momentum, right? So there's different types of momentum, right? There's the linear momentum, so that's the momentum of something that's moving in a straight line. There's also something called angular momentum. That's the momentum of something that's spinning or rotating, revolving, right? Circular motion, that type of thing. Right now, we're not worried about the spinny type of momentum. We're worried about the linear momentum. So, but momentum in general, right? What it means is, I'm going to use Isaac Newton's words, right? This is what Isaac Newton called it. Okay. So if you actually read Isaac Newton's Principia book, I have a copy, and it's surprisingly readable. Like you don't, like he explains everything, because what's sort of interesting when you read Principia is that, well, so, it was originally written in Latin, of course. And, you know, I don't know Latin, so I'm reading the English translation of it. But it's very clearly written. And what's interesting or striking about it is that the uh, you know, he doesn't use words like momentum, right? Because, you know, momentum wasn't even really defined as a concept yet. You know, I mean, this is 1687 is when the Principia was published. All right. So he's always using, you know, he's using little phrases to describe things, right? So he talks about quantity of motion, um, you know, and stuff like that. So I'm just going to sort of reuse some of those words from that book here to explain what it is. So that's what it is. It's the quantity of motion that something has as it moves. And so we can sort of think of it also, right? If I use my words here, it's also how much of an impact. Whoops. How much of an impact do you get? How much of an impact do you get when you're hit by this object with this momentum, right? How much of an impact do you get when hit, right? So imagine an object that's flying with a certain amount of momentum and you stand in the way of it and you get hit by that thing, right? So you'll get hit with a certain amount of impact, okay? If the object has more momentum, then you'll get hit with more impact, right? It'll do more damage, right? When it hits you, okay? So you can quantify the amount of an impact that you get when hit by a moving object as the momentum of the object. And so how is it defined? So the definition of momentum is defined like this, right? It's a vector quantity. Yeah, we got an ambulance going by here. Sorry about that. Okay, so the momentum is defined. It is a vector quantity. It's a vector quantity. So I draw it with a little arrow on top, and it is defined. Okay, the ambulance is coming back. Oh, all right. Hopefully, hopefully there isn't too big of a problem there. All right, so we got the momentum, and it is defined as the mass of the object times the velocity, right? So you see, if you have a more massive object moving faster, right, it's going to have a bigger impact on you, right, if it hits you. You see? So you'd say that this object has actually a higher quantity of motion, all right? So now this is to be distinguished from kinetic energy, all right? So this is momentum. This is momentum right here. And actually, to be more precise, this is actually linear momentum. This is actually linear momentum. Angular momentum is defined differently, but we won't worry about that right now. Okay, so this is linear momentum. And kinetic energy, of course, if you remember from the last two chapters, looks like this: 1/2 mv squared. Actually, just from the previous chapter. Okay, and so kinetic energy is also kind of, right, the more motion something has, the more kinetic energy it has, right? Kinetic energy is the energy of motion. But we don't think of kinetic energy as the quantity of motion, because kinetic energy is a scalar quantity, right? It's a scalar quantity. So whether you're moving, you know, with a certain speed to the left or to the right, you know, or at an angle, you know, the kinetic energy is going to be the same, you know, if the speed is the same, because it doesn't care about direction. But if you do care about direction, right, and you do want the vector nature to be expressed, then you'd be talking about this quantity here, the quantity of motion, which is the linear momentum. Okay, so this is the difference here. So now, so you get it by multiplying a mass by velocity, and the SI unit of momentum is known as the kilogram meter per second. Okay, so I always say that this is an example of a unit that nobody wants to take credit for having discovered, right? Because other units, you know, we credit people by naming the unit after them, right? So like a Newton, you know, is named after Isaac Newton, right? Or like you know, in physics 220 you learn about amperes and volts, right? You know, or coulombs, right? These are all named after people who came up with them, right? Or came up with the physics that led to them, right? But here, this one, nobody wants to name it after anyone, so we just call it kilogram meters per second. So but alternatively, it could also be, it is sometimes expressed in kilogram meters per second, or it is also expressed as Newton seconds. Okay, and so why is that? Because you see, a Newton is a kilogram meter, right? A Newton is a kilogram meter per second squared. And then, so that's a Newton. And then we times it by seconds. And so you see, it's the same thing. The second cancels with inverse second squared. So you get kilogram meter per second, just like what we started with. So you can either talk about momentum in kilogram meters per second, or you can talk about in Newton seconds. Okay, and I already said that it is a vector quantity. And so if you have a single object moving with velocity v that has mass m, you times the two together and you get the momentum. If you have a collection of objects, also known as a system of n objects. So if you have a system of n objects, why, in that case, you can add up all the momenta. So the total amount of momentum that you get by adding the momentum of number 1 to the momentum of number 2 to the momentum of object number 3, and you keep doing this until you have added in the momentum of object n. Okay, so for a system of n objects, you just add up the momenta, and these are all vectors, right? So you got to add them head to tail, right? You got to add the vectors, right? The way you add vectors is you place them head to tail and then you add them. And so if you have a whole bunch of vectors, you got to place them all, you know, head to tail, right? And then you add them all up, you get the total. Okay, and the total is also a vector. It's the resultant that you get when you add up all these individuals. Okay, so that's basically how you do it. It's momentum, and it is useful. So let us see how it can be used. Okay, let us see how to use it. So let me do this. All right, this is going to be very interesting. All right, so you see here, what we can do is now, with the definition of momentum this way, we can ask ourselves, what is the most general form? Yeah, you can ask yourself, what is the most general form of Newton's second law? Okay, so so you see, up to now, you've seen Newton's second law looking something like this: F net equals mass times acceleration. This is the form that you've seen up to now, but this is really a special case. It's a special case because This is true if the mass is not changing, okay? If the mass is fixed, then you can use this. But if the mass is changing, then, it doesn't quite work this way anymore. You got to do some things to account for the change in mass, right? And so, when does this arise? This arises when they send those rockets off to the space, right? So when you did the free fall lab, you watched the rocket video and the rocket took off and then it starts, so it's, first of all, it's spitting out the fuel, the exhaust gases, right? It burns the fuel and the exhaust gases go flying out the back, right? So the rocket is losing mass as it flies, right? And then at some point they do the MECO thing where no, what do they do? They throw away the main stage and it drops down, or it goes back down to land or something. Right? And so the thing that keeps flying, the part of it that continues going, is now a heck of a lot lighter because they jettisoned the other part, right? So in that case, you say that the mass is changing, right? Because some of the parts of the rocket are falling off and going away. So in that case, you can't do this anymore. So the most general way to write Newton's second law actually involves momentum. So you do this, you go F net is equal to the change in momentum over time, okay? And so this is known as, or put another way, so we'll use the fact that P equals mv. So this is the same thing as asking for what is the change in m times v over some interval in time, okay? So the net force on an object produces a change in momentum in a certain amount of time, right? So put another way, the net force on an object is equal to how fast its momentum is changing, right? So remember, forces produce changes to an object's motion, or at least a net force does. A net force produces a change to an object's state of motion. And so changing the motion is changing the momentum. So now what we're going to do, we're going to take a look at this here. So it turns out that if you have a change of a product of things, it ends up looking like this, right? So I'm just going to write this down. I'm not going to prove it. This is not a math class. This is a physics class. We're just going to use these math results and we're not going to prove them because we're doing physics. We're not doing math. I know sometimes it's hard to tell the difference, but there is a difference between physics and math. They aren't the same thing. Okay, so here we go. We have this. If you have a change in this thing with the product, it's this plus this, all right? And so usually delta M equals 0, okay? Usually the mass of the object is not changing, it's staying the same. And so in that case, if delta M is 0, then this part is 0. And so then you get M delta V over delta T. But remember, the change in velocity divided by the change in time is the acceleration, right? So this becomes equal to ma. So you see, and so we recover the special case of Newton's law, which is Newton's second law, which is the case when the mass is not changing, okay? So this is when the mass is not changing, you get this. But if the mass is changing, this part is not 0, and so now you have to do stuff, okay? So that's what happens, all right? So now in general, though, this is what we like to use as the general. This is the general form. This is the general form of Newton's second law. And so in this chapter, we're going to be considering it this way. In this module, we're going to be using Newton's second law like this, okay? So we're not going to be using it like that. In this module, it's going to be like this. Okay, so we're looking for changes in momentum. All right, we're looking for changes in momentum. Now, it's still true, by the way, even if your mass is staying fixed, it's still true. If the delta M is 0, then delta P is just equal to M delta V. Okay, so in the case where there's no change in mass, this is true, right? And so this still holds, right? It still holds. It's just another way of expressing this same thing. Um, you know, um, they become the same when the mass is not changing. Okay, but this one is true regardless, right? This one is only true if the mass is not changing. This is true in all cases. This is general, right? So it's true in all cases. Okay, so all right. So now what we do is we take this equation here, and then we rewrite this a little bit. So we take this, and then if we multiply both sides by delta t, we get F net delta t is equal to delta P. Okay. And so now you see the change in momentum that you get from a particular force is found by multiplying that force by the time over which the force is active. Okay, that's what this says, right? So a force produces this change in momentum if you allow it to act for this long. Okay, that's what it means. And so what we do is we take this and we define something called the impulse. And so the impulse is defined. We use the symbol J to mean impulse. It's also a vector, and that is equal to the net force on an object times the time. So you see Newton seconds, right? Remember I said momentum can be thought of as being in kilogram meters per second or Newton seconds. So here you go, Newton seconds, right? Force in newtons, time in seconds. Okay, and so this is this. So the impulse J is equal to the change in momentum. All right. So an impulse is a change in momentum. So the momentum of the system that you're looking at, it went from having one value to having a different value, right? So you look at this change, you say, okay, the momentum changed this much. Well, that equals the impulse, right? So so systems don't just change their momentum just like that. There has to have been something that happened to cause its momentum to change. And so that thing that happened, of course, is this force here, right? The force, use the force, right? So a force comes along and it acts on the system and it produces a change in momentum. And you can ask, well, how much of a change? Well, that's the impulse that resulted from the action of this force. Okay, so that's impulse. So now, so this equation, by the way, is technically only true if the net force is not changing during this period of time, right? So let me say this guy, this equation, actually, no, sorry. What I really mean is, let's see, what I really mean is this equation. Yeah, this equation. And this one as well. But this one, let's consider this one for a moment. This equation, okay, this equation is technically only true if F net is constant, right? And what do I mean by constant? What I mean is that this F net, the net force, is not changing during this period of time, right, over which it is active. If it's changing, then it becomes a bit more complicated. You've got to do some calculus to do this properly, but we're not going to do any of that. We're going to sort of assume that, yeah, the force is basically constant. And you can do that provided you do the following thing. So what you can do is, right, is that, okay, so what you have is you have a graph. Okay, so this is your time axis, and this right here is going to be, let's say, the magnitude of the force, of the net force, the magnitude of the net force, okay? And so what we're assuming is that at time 0, the force is there, and it lasts for a specific amount of time, and it's gone, okay? And then during this time, the force is unchanging. So let's see here. So what we got here is here the time is equal to delta t, right? So here t is equal to 0. Here t is equal to delta t. And so during this time interval, the force was flat, right? And so what you do is you say, okay, what is the impulse I get? I just simply take this constant and I times it by the amount of time, and then I get the impulse, right? So that's what happens. However, in reality, this is rarely the case. What usually happens is something like this, is that, like let's say two birds fly at each other and they collide or something, right? What's going to happen is you want to know how much impulse was provided by one bird to the other. Well, in reality, it's going to look something like this. It's going to look like this. There's nothing. Then, then it does this, right? Something like that. Okay. So it's going up and down and up and down, right? It's changing during this time interval. It's not staying flat. Okay. And so what you do is you define an average force, right? And so what you do is you say, okay, yeah, so the impulse, or sorry, the amount of force was changing over this time, but what I'm going to do, I'm just going to take, what I'm going to do is just going to take an average, right? An average over this, an average of all these bumps. I'm going to take an average over the time, and I'm going to assume that the force just had the average value the whole time. And if you do that, you get the same answer, okay? And so what we're going to do is we're basically going to, we're going to simply assume, we will assume that F net is equal to F average, right? So that's the average, over this time. And so the impulse then is simply going to equal the F average times the time. Okay, and I've dropped the vector symbols because, we're just talking about magnitudes here. We're just talking magnitudes here. Okay, so that's what we're going to do. We're going to simply use F net and F average interchangeably whenever we're talking about impulse, because you can do that, you get the right answer. And so, those of you that are curious about this, you can see that if you take the constant force and you times it, right? So that's this height is your constant force. So we'll call this F0, or actually let's call it F average. Okay, that's this height. And then this width is delta T, right? So you can see that if you take this height times this width, you basically are finding the area inside this rectangle, right? And so this is true in general. If you have a force that's varying in time and you want to know how much impulse it provides, you simply have to calculate the area under its curve, right? And the curve is the function, it's the curve of the force as a function of time. So if you have the area under that curve, that gives you the impulse. Okay. So let's see. So here, let's do an example. Let's do a quick example here. All right. Let's do an example. Okay, I'm just making sure everyone's still here. All right. You've been awfully quiet. Just making sure you're still on there. Okay, so let's do an example. Let's do an example here where we look at impulse. All right, let's see here. Let's do an example. All right, yeah, that looks pretty good. Oh yeah, here we go. All right, so let's see. Go back. Okay. All right. Everyone's still here. All right. That's good. You know, I haven't caused anyone to faint from boredom. Okay, so well, I don't know. Maybe you're fainted over there. I can't see it. Okay, so let's see. So we're going to look at question number 2 in the homework number 8 as our example here. And so here they've got the runaway train car, and it has a mass of 14,263 kilograms, and it travels at a speed of 7 meters per second down a track. And they want you to compute the time required for a force of 1,454 newtons to bring the train car to rest. Okay, so let's have a look. Okay. All right. Are you saying yes? You're so bored that you fainted? No, I'm kidding. All right, let's see. All right. Yeah, so I mean, you know, this isn't all that boring, I think. You know, this is one of the less, I mean, this is a, you know, there's physics that's boring and there's physics that's, you know, not so boring. I think this isn't all that boring. Okay, so let's see. We have got, yeah, I think the physics of, like, you know, what we were doing with the elasticity of the thing that bends and it squishes, I don't think that's all that interesting. But I don't know. Maybe some of you have different opinions. Okay, so what are we doing? This is homework 8. Okay. Oh my gosh, what am I doing? All right, homework 8, question 2. Okay, so we are trying to stop the train. All right, but we only have a 1,454 Newton force. So, and we want to have the train's momentum go from some value down to 0. So we're talking about delta P is equal to F net delta T. Okay, and so we want to know, well, no, we want to know how much time we have to apply the force in order to produce a desired impulse. And so, so what does that mean? Well, here, let's see. We're told that the net force that we have is equal to 1,454 newtons. And we are told that the initial speed of the train is 7.00 meters per second. And then we are told that the mass of the train is a solid 14.263 metric tons. Okay, so that's 14,263 kilograms. All right, so now this is the information we have. And so what they want us to work out is how long is it going to take to stop the train? So stop the train car, to be precise. So what we can do is we can go ahead and solve this guy. Actually, wait. We'll put in a little bit more information, then we'll solve it for the time. So this is delta P. So what is delta P? Delta P is known as the change in momentum. So this thing goes from having some momentum because it's moving to being at rest. So the final momentum is going to be 0 because when you're at rest, your momentum is 0. And then your initial momentum. So remember, delta P is final minus initial. So you know what, here, let me be more explicit. Okay, so delta P is P final minus P initial. Delta P is equal to P final minus P initial, which is equal to F net times delta T. All right. So that being the case, let's go ahead and solve for delta T. Then we'll start plugging things in. Yeah, let's do it that way. So delta T, I'm going to divide both sides by F net. So I get delta T is equal to P final minus P initial divided by F net. Okay, so now we go ahead and we plug in, right? You see the impulse we want to provide is the change in momentum to take the train from what it had to start with to 0. So we plug in 0 kilogram, 0 kilogram meters per second. And then we have, what we got over here? Oh yeah, we got 14,263 kilograms, because remember, P equals mv. Okay, so this is the mass, and we're going to times that. We're going to times that by 7 meters per second. And then we have to divide by F net, which is 1454 newtons. Okay, now there is one thing we're going to have to do, and I hope you will allow me to do this. So consider what we're doing. We have a train, right? You must allow me to do the following thing. So we've got the train car, and it's going like this. Okay, V0. The train car is going like this, and then we stop it, right? So the momentum P initial is also going in the same direction, right? Because remember, velocity and momentum are always parallel to each other, right? Because the mass is a scalar, and you multiply a vector by a scalar, you get a vector that is pointing in the same direction. Okay. I mean, unless the scalar is negative, right? But if it's a positive scalar, which is what mass is, there's no negative mass, as far as we know. So the momentum and the velocity will always point together in the same direction. Okay, so the momentum initial is like this, but the final momentum is at rest. So what does that mean? That means our impulse has to be that way. Our impulse, in order to make this guy go from pointing to the right to not pointing at all, we have to apply a change in the momentum that is in the opposite direction. Okay, and so we're going to say that to the right is positive, to the left is negative. And so, so if the impulse is that way, and remember, the impulse is the force, the net force, times delta t. So that means that the impulse and the net force are going to be in the same direction. Why? Because time is usually not negative, right? Time is usually positive. It's usually not negative. So so the net force and the impulse must point in the same direction. So the net force here, the net force is going to be like so. So this means that you must allow me to place a minus sign down here, because I want the force to point in the opposite direction as the initial momentum. And so when I do that, these minus signs cancel. Minus and minus, they cancel, right? Because 0 minus this, right, would have left me with a negative. They cancel. So I have 14,263 times 7 divided by 1454. And that works out to 68.7 seconds. Okay. And so you can see here, here I had kilogram meters per second squared. So the kilogram meters cancel from top and bottom. And then I have inverse seconds on top, but inverse seconds squared on the bottom. And that just leaves you with seconds overall. So this is 68.7 seconds as your result for that problem. Okay. Okay. So any questions about that one? This is homework 8, question 2. All right, sounds great. Okay, let us now move on to the next topic. Let's see, what is the next topic? Ah, yes, conservation of linear momentum. All right, let's take a look. Conservation of linear momentum. All right. Conservation. Okay. Actually, you know what? So yeah, since we're doing these longer Zoom sessions, I think it's probably a good idea for us to take a short break, between topics. So let's do that. Let's take a 5-minute break, and then we'll come back and we'll dive into conservation. So let's take a 5-minute break here, and so let's do that. take a 5-minute break. So we'll come back at, let's see, I have 10:22, so 10:27. We'll come back. 10:27. All right. Okay, we're back. All right, so let's see. We were just beginning to look at conservation of linear momentum. Okay, what does it all mean? All right, let's see what it means. So what we have here is yes, what do we have? Right. Okay, so you see here, we've got something that I will write down here. We've got conservation of linear momentum. So, this is just a fancy way of saying that momentum is a constant, right? If you have an isolated system, right? So what does this mean? Yeah, I realize this is it's a lot of words, big complex words to say something that's a fairly simple idea. So let me see if I can explain it simply. So if you have a system, right? And so by a system, I mean like you've got like you've got billiard balls, or you've got like the birds that collided, or something like that. You've got a system of objects that are interacting, okay? And so let's say they're bouncing, they're knocking into each other, right? So you got these objects and they're knocking into each other, but these objects, they form a system of interest, right? But if this system is isolated, which is to say that it is free from outside influences, right? It doesn't have like external forces acting on it. Then in such a system, the total amount of momentum in there is going to be the same. It's going to stay the same until that system is acted upon by an external unbalanced force. So if you have an isolated system, in an isolated system, what you have is there is no net external force acting on it. So we say that um, in the isolated system, you have F net is equal to 0. Okay, it is equal to 0. So that means there's nothing acting on it, that leaves that provides a net force. And so what does this mean? This means that delta P over delta T for the system is also equal to 0. Recall that Newton's second law now looks like this, right? Now that we understand momentum, this is how we write Newton's second law. Okay, so if F net is 0, then this is also 0. And so if you take the total change in momentum for the system that you're looking at, if there's no force acting on the system, no net force, no net external force acting on it, why then this change in the system momentum per unit time is going to be nothing, 0. And so this automatically implies, if we times both sides by a delta T, delta P, again, for a wonderfully isolated system, is going to be 0. So what does this mean? This means that if you have an isolated system, which means that there's no net force on it, means that the momentum of that system is never going to change. Never going to change. The only way to get it to change is if this net force becomes not zero, right? If you have a non-zero net force, then yes, absolutely, you're going to see changes in momentum. It's going to happen. But as long as that net force is zero, there is not going to be one change in the system momentum, right? Now, it is true, though, that individual components in the system, they can be having changes in their momentum, right? They can be changing. But if you add up all the changes in momentum of all these system components, you're going to get zero, right? They have to all cancel, right? If they don't, then it means that there must be some external force that you didn't notice, right? It has to be there. Okay, so so we call this the principle of momentum conservation. Right? So that basically states that if you have an isolated system, the total change in momentum for that system is just going to remain at zero. Or put another way, the total momentum in the system is going to remain the same. It's going to remain the same, or some people say it is conserved. That just means it stays the same. So we can look at, let's see, what do we got here? Yeah, okay, so let's see. So what does this mean in a practical sense? So they show an example in the book where you have the two cars. So there's car A and car B. So I don't know, let me see. So you have a car here. Let's see, this is car number one. And so car number one is moving. Okay. Let's see. And so they call this, I think they called it V. Or no, sorry, that's not right. That's not right. What they called it was they said, okay, it's moving, and the quantity of motion that it has is known as P1. Okay, so it's moving, and then it hits the little minivan. Okay, it hits the little minivan number two, and so it hits it, and then after, right? So they hit, and then it goes bang, right? And then the next thing you know, what's happening is that this guy is now moving with a new momentum, right? So I think they call this P1 prime. Okay. And then this guy, you know, he gets knocked into, so he moves, right? So he starts out at rest. And then after the collision, now this guy is rolling forwards. Okay. So now this guy has some momentum and they call it P2 prime. So they use this notation in the book. They use sorry about that. That's my phone. They use the prime notation, right? These little apostrophes up top here. They use that notation to indicate after the collision, right? So so initially there's some momenta of the system, and then after they have different momenta because they collided, they interacted with each other. Okay, and so so we can ask ourselves, how much did the momentum of number one change as a result of the collision? So basically what we would write is delta P1 is equal to however much force number one experienced multiplied by the amount of time that the two cars were in contact with each other, right? So they touch, and then, you know, they as they collide, they touch for a moment, right? They exert forces on each other, and then they move apart. Okay, so during that time of impact, there was this impulse that was provided that resulted in this change in momentum for number one. And for number two, same idea. So the force that number two experienced is F2, but they're in contact for the same amount of time, right? Now, what we do is we go to Newton's third law. And Newton's third law says that F2 is equal to the minus of F1. So if you push on something, it pushes back on you just as hard, right? This is just how forces work in nature, right? You push and it pushes back. Whatever you push on is pushing back, okay? Exactly as hard as you're pushing on it. So this is gonna be true. So then what we do is, if we want to add up, if we want to calculate the delta P system, here, let's do that. So for our two cars that collided together, the two cars that collided, so the delta P for the system is going to be, you have to take all the changes in momenta and you add them together. This is how you get delta P for the system as a whole, right? So these cars are isolated. There's nothing else happening to them besides they collide, right? So we're neglecting the force of friction, you know, from the wheels on the road, right? We're neglecting all of that. We're just saying that these two cars, the only interaction they had with anything else was the interaction between them when they collided for a brief moment. So if we plug in the numbers here, or plug in the expressions, so we have F1 F1 delta T, and this is going to be F2 delta T. But it is true already, I said that F2 is equal to negative F1. This is also known as Newton's third law. Newton's third law. So now we have F1 delta T. So we plug in minus F1 for F2, so we get minus F1 delta T. So this minus itself, hey, that's zero. So you see, delta P for the system is going to be zero, because anytime these guys interact with each other, they're each interacting back against the other one just as hard, and these effects, they all cancel for the system, right? If you take the system as a whole, all of these changes in momenta are always going to cancel each other. They're always going to cancel each other when you add them up. And so anytime that you see, let's say you're observing a system and you see that you calculate the delta P of the system and you find that it's not zero, right? So that means that it's not isolated, right? That means that it's interacting with something else that is, you know, changing its state of motion, or changing the states of motion of the elements inside of it, right? So, but as they correctly point out in the book, if you have a system where you calculate the delta P and you don't get zero, that just means you can always define a bigger system, okay, to include the thing that's providing the force that's causing the delta P of the smaller system to not be zero. if you make your system bigger to include the things that's producing the net force, then you find that, you know, that you do this again, and then you get delta P 0 for the bigger system that includes everything. Okay. And so, you know, this keeps going all the way up to the universe itself, right? So we believe that the universe as a whole has the same momentum today as it did from when it had the Big Bang, right? So, and the total amount of momentum in the universe as a whole is fixed. It's never going to change. Okay, at least that's what we think. So, so there you go. So if you're finding you get delta P system is non-zero, if you make your system to include the entire universe, it's going to be 0. Okay. So okay, so that's what happens. All right. So another way to put this is that if delta P for the system is equal to 0, another way to put that is to say that, let's see, P1 prime minus P1 plus P2 prime minus P2 is equal to 0. And why? Because delta P1 is equal to P1 prime minus P1, and delta P2 is equal to P2 prime minus P2. So that's what happens. So now, so what does this mean? You can do a little bit of algebra here. So I'm going to add P1 to each side, and I'm going to add P2 to each side. So I get P1 prime plus P2 prime is equal to P1 plus P2. So this is P, the momentum for the system, and this is after the collision, and you see it's equal to the momentum of the system prior to the collision. And so you see, so this is another way of saying that delta P for the system equals 0. The system at the end, the momentum for the system at the end is equal to the momentum that it started with. And if you find the mismatch, it just means your system isn't big enough to include the things that are acting on the system that you were looking at. Okay. Okay, so that's good enough. All right, so we got our principle of momentum conservation. So yeah, this is basically another way to express the so-called principle of momentum conservation. Okay. Principle of momentum conservation. That's this. All right. And, you know, this only holds, of course, for an isolated system. Okay, so that means one in which there's no external forces, no net external force acting, no net external force. All right. So now let's take a look at collisions. Oh, okay, looks like I only have 3 minutes left. All right, so okay, let me stop there. Are there any questions? All right, so I guess, yeah, it's going to take me a while to explain this. Okay, so I think we'll just end it there then. So we will see you again on Thursday.
Okay, thank you, Professor.
Thank you.
Thank you, Professor.
Thank you. Have a good one.
You too.
Thanks.